Hi guys, thanks for coming to this afternoon session. We have around 9 topics around the SONiC ecosystem deployment improvement on top of it. The first one will start with Lihua and me. Thanks for coming to today's talk. My name is Xin Liu. This is Lihua. We are engineers from the Azure Networking, Microsoft. We are here to presenting the SONiC community to update everyone what's going on in the community. For the ones who are new to this project, this is a cheat sheet for you to understand what's this project so that you can enjoy the rest of the conversation. So 5 takeaways from these slides. First, this is an open source NORS running on Switch. This is a Linux box, so that you can use familiar command line, user interface, and OS to run on your hardware. Second, it is hardware agnostic through SI. SI is a switch abstraction interface. Because of SI, we can use the same NORS operating system to control different hardware platforms. Third is containerized network stack. Because we put them into container, it's well isolated, so it enables you to have the 4th takeaways. It's very easy to customize and extend to your new scenarios. 5th, you can run all the open source toolings, management and Ansible testing automations on top of it. It has a lot of opportunities so for you to extend. The community has always been growing. These are the members has been with us since last year. With that, we are going to welcome a few new ones join since last OCP. First, here is the hardware platform like Juniper, Alpha Network, Mitag, Ruijie. They support SONiC on top of their hardware platform. The second, we have new new companies from user space, from application space. They contribute user scenarios, feedbacks, bug fixes, pull requests. These are Baidu, Didi Taxi, and Jingdong Cloud. We also have companies from the service point of view join the community. AVSnet, Citrio, Wipro, and also student researchers from the Hong Kong University of Science and Technology conducting research on top of SONiC. So what we have done, this is a small slide to update the feature updates from the last OCP. There's a lot of things happening. For example, in telemetry part, we build the gRPC as a pipeline for streaming telemetry. We provide a data plane telemetry extension for some of the platforms to run data plane telemetry. Also, we are going to provide virtual paths so that the data can be structured out. You don't need to query or pull them one by one. It can be streaming out in the nicely structured data. In the platform management, we are beefing up the sensor transceiver monitoring. We are adding dynamic parameter tuning. Knowing the cable length, we are able to dynamically tune the set. And also, we are refactoring the platform monitoring to be PMON. We are doing a lot of work in the reliability space. One of them is to improving from faster reboot to warm reboot. We are going to the deep dive later in this session. Also, we are doing system work that to upgrade the whole kernel to be the 4.9 Debian. The native is the kernel. We are upgrading all the containers. We are doing the security patches. These are not all. We have a lot of things. A lot of things happened actually since last OCP. Also, in the community, we have new platforms joining. Juniper's PTX, which can provide the 1 million route on the switch. We have SONiC enabled on Broadcom Tomahawk 3, Jericho 2 switch, on Mellanox Spectrum 2 switch, Facebook Mini Pack is able to support SONiC, as well as Marvell 12.80 Falcon-based switch. And what's unique is they are ARM-based. These are first ARM-based switch that support SONiC. As well, the last one is Innovim ASIC. SONiC is able to run on top of Innovim ASIC. We also had fun. It's not only work. We had 3 workshops globally here in Flex last August. Last October, we had a workshop in Beijing. 2 days ago, we had 250 people workshop at LinkedIn, and we also had a hackathon. People joined. These are the winning teams. How happy they are. So with that, we are going to deep dive into one of the areas that we heavily invest since the end of last year. This is a very important feature to all the users of SONiC. With that, I'm going to give to Lihua.
Thank you, Xin. Well, I'm going to talk a little bit about warm reboot, then I'm going to move on to the SONiC support for disaggregated chassis. Both are truly community work that actually I won't be able to go to a deep dive, as she mentioned. It's going to be a shallow dive, because those things are the community actually spent quite a while to work out, right? And you see that many people across different companies has been working together as one team, right? Sitting literally in the same office overnight and get things hashed out, right? So really a lot of effort put into this. So before I talked about warm reboot, right? You know, SONiC has been supporting this idea called fast reboot for a while, right? Fast reboot, so I have to go through that a little bit so you see the context of this. Right, in fast reboot, right, it's mostly about a trick that basically we don't reset the switch ASIC until the OS has come back from reboot, right? So the sequence has been changed from the code reboot, right? So the OS went reboot first, while the routing stack and the data plane kits are unchanged through BGP graceful restart, right? So the control plane may go down, and typically it's less than 90 seconds. Then the OS come back, right, and the data plane gets resetted. And during this period, there's a lot of optimization work that gets the data plane disruption time to less than 30 seconds, right? And what is warm reboot, right? Warm reboot is basically that we have the idea that we really need to push the downtime to be less than 1 second, right? In many cases, we're able to get to 0 downtime, right? And this team came out with a lot of pretty innovative ideas to get that achieved. But the main difference between the warm reboot and the fast reboot is actually that the chip, when it comes back, the stack understands the difference between the ASIC state and the actual desired state and able to compute the differences and through some comparative logic and able to keep the ASIC running and minimize the downtime. Here's how it actually works in the architecture, right? So basically, you see the warm reboot, when you issue the warm reboot command, it stores the appdb and ASIC DB on the disk, right, the persistent drive. Then when the OS come back, right, Redis basically will restore the app and ASIC DB after reload, right? For people who understand the architecture, there's this orchestration agent, which is essentially a compiler from the appdb and generates the ASIC DB, right? In the ASIC DB, it all stores the side objects. Right. And you might wonder, like, what over here, right? The number 3 step is actually OA will read the FDB again and compose a new ASIC DB. Now you have the ASIC DB you restored from a disk, which is old ASIC DB, and you have a new ASIC DB. You might wonder, like, why do we have this compilation again, right? If the FDB didn't change at all, why do you have to recompile again, right? The real reason is that every code in this through the OS upgrade might changed, including the orchestration agent, which is the compiler itself. Right? So for that reason, there's a new compilation, and then you might have old ASIC DB and a new ASIC DB. Right? So SYNC has been enhanced to understand this and compare the old versus new ASIC DB and apply the differences to the hardware. Right? And while all this reconciliation is being done, the application are waking up in parallel. right? Because we want to minimize the application downtime as well, right? So, and in this case, right, they may have staged changes to the application DB already, right? So those changes are left in the staging area of the application DB, right? And then OE, in this case, is actually relatively simpler. It just understands that this is normal change because application requires some changes, right? And it basically updates ASIC DB, and SYNC does its normal job of making sure the ASIC DB and ASIC are in sync, right? So this is how we complete the warm reboot. Right. Here's a little bit demo. Not sure if good. The sound might be a little bit too low. There's no sound. Where's the sound? Okay, I'm going to talk through this, I guess. Yeah, there's no sound. It's okay. Yeah. So, okay. I don't know whether people can see this clearly, but okay. So this is pre-recorded, so it's a little bit challenging here. Yeah, this is recorded in voice, so why don't I have you talk?
Can we rewind a little bit so that I can talk from the beginning? So I guess probably best.
Go ahead. Yeah.
Thank you. Hello, everyone. Welcome to the SONiC warm reboot demo today. On this picture, we are showing the topology of the warm reboot system. The red switch in the middle is going to go through the warm reboot. What we're trying to show you today is that while this switch going through the warm reboot, the I/O between servers and I/O between server and T1 switches will continue to flow without glitch. And yeah, let's take to the system. And on the top right corner, this is our I/O monitoring and I/O generator. So on this screen, we can show that we're showing that we are pinning the data plane as well as the control plane. And so we're trying to, we're pinning from T1 to server and server to T1. Those I/O are testing the control plane. Data plane, excuse me. And the next pinning session is pinning the DOT itself, so we make sure that we know when the control plane went away and come back to life. And now we issue a warm reboot command with a -v option so that we can see a little bit more action, internal action of the warm reboot itself. And the first thing happening here is that we stop BGP session. And with that, we see that on the bottom left corner, this is from a peer side, we're watching the BGP status. And the BGP state changed from established to idle. And because BGP graceful restart kicked in, so we don't see routing entry get removed. On the bottom right corner, we are watching, on the peer side again, watching the lag status port channels. And the port channel has been up for quite a while. And what's important, we want to show you is that the port channel will continue to be up during this warm reboot. And on the I/O monitoring, we noticed that the control plane went away already because we're just trying to start booting to the new image. And that's reflected by the fact that the DOT ping I/O stopped going through, but the data plane I/O is still going very strong. That should continue throughout this warm reboot. And we also noticed that the lags still continue to be up. The uptime is continue increasing instead of resetting. So now waiting for our BGP sessions to come back to life. And we see a few log entries saying that RLDP has been reset. RLDP protocol itself is stateless, so we don't really care about the get reset. But as I said before, the most important thing is that the routing entry didn't get removed. That's the reason why we could have continuous data plane I/O flowing. And now our control plane come back to life in a little while. So our data plane continues to forward I/O, and in a little while, the BGP session is going to come back to life. So we're patiently waiting. And I/O going strong, and lag status still up. Now I think we have IPv4 BGP session come back to life. And IPv6 take a little bit longer, but not too much. It should come back almost right now, please. Yes. So the BGP sessions come back to life, and as I said, there's no log entry showing that the BGP peer removed the routing entry towards our switching middle. So that's why we have data plane continue to flow strongly. That is the whole demo. Thank you very much. Have a nice day.
Thank you, Ying. Yeah, so you can probably tell that we're very obsessed with this data plane downtime, right? And we try to reduce it from 30 seconds and 1 second to 0, right? But I think with all the good work, bears a question: is this really enough, right? We're not really done yet. What about the control plane, right? If you look at the CPU disappeared for a little bit, right? And the CPU, if you think about the switch CPU, it's not only the control plane for the switching ASIC. It actually provides quite a bit of peripheral utility functions to its neighbors, right? For example, if you have a server below that requires ARP, the switch CPU needs to respond to the ARP request. If there's a DHCP boot P request, the switch CPU needs to respond to it, to relay it, right? What do we do about this, right? And you might argue that, oh, I'm just going for a vacation. This thing needs to survive on itself, right? But maybe that's not the best answer. Is there anything we can do there, right? And leveraging the existing work on SONiC, on Everflow, and the certain ASIC behavior, we actually came up with this thing called a control plane assistant, which is upcoming yet, right? Basic idea is very simple, right? That a CPU can ask the ASIC to pound a packet to the CPU, but you can also ask the ASIC to mirror a packet to some remote location, right? As long as the IP reachable via ES-span. And we use that heavily in the feature called Everflow, right, for diagnostics. And you can also configure the ASIC to see that if you're receiving packets, encapsulated packets from certain IP address, you can decap and forward it, right? So then you have a two-way communication, right? You have a ASIC control plane assistant sitting somewhere remote in your network, as long as it's IP reachable. And you can ask the assistant, from the ASIC to assistant, you can do the ES-span mirror, and the assistant to the ASIC communication, you can basically encapsulate the payload and ask the ASIC to decap and forward to the necessary neighbors. You can use that to finish the ARP protocol, for example, right? So that's something still in the works, but I think that I just want to show you that how obsessive we are about any data plane or control plane downtime. Right? We're finding all kinds of solutions to deal with it. That concludes the first topic. The second topic is something that actually often asked in the OCP community, is that when would SONiC support chassis, right? And this part, we're going to talk about the SONiC support of disaggregated chassis, right? And why do we want to work on this, right? Again, we have talked about many times that SONiC has been powering Microsoft Azure network at a cloud scale, right? So it's doing a decent job at the T0 and T1. Typically we use pizza boxes there, right? Single ASIC devices there. But this is not enough. Our tier 2 and tier 3 are typically large chassis, right? And what is the challenge there, right? What is the challenge there? We do chassis for a lot of reasons, right? The reason is that we like the power efficiency, we like port density, and typically the chassis have a backend ASIC that has large tables, very low table scale, right? So that it can control the cost. All these things we still like, right? It's not wrong choice, right? We still like those. But what we do not like, right, is that typically inside the chassis, there's no standard definition of the topology or even the connectivity, right? And use proprietary protocols and packet format that makes it's very difficult for when people need to diagnose and troubleshoot, right? For example, it's pretty difficult for you to think of how do you do a packet capture on the inner fabric of the chassis, right? And even if you can do that, the packet format is different. Not many people in the world can actually understand the packet format, right? So it's very difficult to deal with. The second thing is that the switching mechanism and the load balancing algorithm used internally in the switching fabric is typically not open to the public, right? So it makes its own decisions. It has its own brains on how do they do load balancing. And as a monitoring, as an operational team, is it doing the right job? It's very confusing, right? Sometimes you think it's doing the wrong job, but they're actually doing the design job, or sometimes vice versa, right? So that's a challenging part. So really that our focus, right, is that we want to propose a model for SONiC to support disaggregated chassis, that we do not want to move away from the benefits the chassis provides us, but give us a solution there, right? So the first thing is that would like this chassis to be a class topology with Ethernet ports. This is very much aligned with what Facebook has been proposing for years in terms of six-pack, backpack, fabric aggregator, right? So we are not new here, right? And but in order to preserve the backplane chip to be a low table scale chip, right? We're proposing to use VXLAN as a based switching mechanism, right? As a packet header format. So basically, in that kind of model, each front-end chip is going to be essentially a VXLAN tunnel endpoint, right? VTAP. Then packet inside the chassis internally are basically encapsulated with VXLAN header, right? The real reason for us to pick VXLAN is that this is already a widely adopted standard for the purpose of virtualization, right? So pretty much every ASIC supports VXLAN well. It does a good job there, and it seems to serve the purpose, right? And then internally, when we do the balancing, we stay with simple ECMP for now, right? And in terms of control plane, we decide to go with BGP EVPN as the internal control plane mechanism, right? So basically, the idea here is that we're going to set up one SONiC BGP instance per ASIC, right? And then you have the BGP set up internally, and the front-end SONiC will directly redistribute routes using EVPN, right? So that way, the backplane chip doesn't need to carry all the routes that needs to go to the front-end chip, right? So in case you need a chassis that needs to support large table, you just need a front panel chip to support big table. You don't need to kind of use exactly the same chip at the backend, right? And that probably provides a much better scale overall as well, right? So that's the idea, and our calculation says that we can probably do 1,000+ ports easily with this model, right? So the port mass is probably something that everybody can easily work out. Yeah. So, okay. So Prince, can you? Yeah, I don't think I'm going to have a voice here, so maybe you should go talk about this. Thank you.
Hi, I'm Prince. So we are showcasing the demo of a disaggregated chassis. As you can see, there are 8 switches participating in this demo. There are 5 back panel switches and the 3 front panel switches, which we call the leaf 1, leaf 2, and leaf 3. So we use EVPN in the BGP EVPN and VXLAN in the leaf switches.
Okay, looks like we have more video problem. But anyway, So I just explained this, right, and what we intended to show, and many of you probably have seen this at our booth already, and you're welcome to take a deeper look over there, right? So over here, you see there's a set of leaf device, right, and you see a set of spine device, right, oh, it stopped playing now. Oh, is that, wait, what are you doing? Okay, no, I need to go back, yeah. So basically, what the key point, right, what we want to show here is that the leaf and spine, especially from the leaf, it presents the same ASN number, right, and you use BGP eBGP to talk to the top of rack, right, and all the routes from the top of rack going to the front end chip is actually not reflected in the back end. It goes reflect to the other end directly. So this is a little bit messed up. Yeah.
Yeah, this is the Leaf 2 device where we have VRF and VXLAN configured. You can see that the front-end TOR is connected through Ethernet 32 to VRF master device, which is VNet 1. And there is also a VXLAN configuration. That's the VNI 8000 shown in the slide. This is the BGP EVPN configuration on the Leaf. You can see that there is 2 instances of BGP configuration, one for the default VRF and the other for the VNet. And you can see the BGP EVPN configuration here with the neighbor 3.3.3.3, which is another Leaf in the topology. So let's have a look at the route on the Leaf. You can see the 10.0 subnet for the TORs that is being distributed through EVPN. Now we'll look at the backend configuration of the spine. There's no route to the TOR, so that's the key point here. We don't have routes of the TOR advertised to the backend plane, so it's just the regular BGP configuration. And here we can have a look at the spine BGP configuration. It's a normal BGP. There's only one instance of BGP running in the spines. So this is the packet flow. We are pinging from TOR 2 to TOR 1. You can see on the right side that the ping is successful. And we have also captured this packet on one of the spine where you can see the ping packet being encapsulated in the VXLAN, and that has a VXLAN header with the source and destination IP of the 2 loopback addresses of the TOR, of the Leaf, sorry. And that's the demo board. You can, for any detail, you can visit the booth, Microsoft booth. Thank you.
Thank you, Prince. Yeah. So I'm going to end this quickly. So Dave actually already shared this yesterday at his keynote, and there's a few more items that the community more or less reached agreement, and we're going to focus on working on. And many things has happened already, right? This is started from 2016. And you can see the highlight of warm reboot, official release, EVPN, and MLAG is something that of interest to many people in the community, and the community is actually gearing up a resource to work on this, right? There's many push on the Kubernetes management capabilities, and even in the workshop hackathon demo, there's a project that people are pushing for that. So I think this is going to happen. There's many contributors that are working on RESTful APIs. It's probably more than a few. I think 3 or 4, if I recall correctly. Right now, the RESTful API being established as a standard seems to be going well, but the actual data model are not fully established or agreed in the community yet. But so this is something that the community is actually working on. Right? So this is a kind of quick update. And then you see the bottom that ARM support is coming from Marvell, and Microsoft actually started deploying SONiC on the management switch as well, and we're actively working on chassis. Right? this is all the updates from us. And certainly, like Xin pointed out, there's quite a bit of stuff. We only kind of shallow dived into 2 of the high impact ones, but there are many others that are highly impactful. And hopefully you're going to enjoy seeing some of that and visit the booth. Thank you very much.
With that, sorry, because of we are late, we only take 1 question on this. Okay, yeah. You want to set up?
Just real quick, I mean, how would we get involved in the RESTful API work? I've not seen any visibility of it on the community or the mailing lists. How do we get involved in the RESTful API work?
The question is, how do people get involved in REST API work? Yes?
Because you said there were 3 or 4 people working.
Yeah. So I think there's different proposals on how the REST API should work. I think we can follow the same route as Sai, right? Basically, get people who are interested together and establish that.
So it's all going to happen through the community calls and the mailing list?
That's right.
Okay.
Yeah, that's the intention, yes.
All right, thank you.